Hi everyone. My name is Chris Orwa. I'm a data scientist. You can find me online as Black Orwa, also at blackorwa.com. You can find other things that I do about data science. Currently, I work for I&M Bank as a lead data scientist. I also write data stories for Nation Media Group, plus I do other things. One of them being this, workshops, talking, etc. I got informed about this, the Zindi challenge about ambulances, and it's just one of those things that you read and then they kick your mind. You start thinking about how we could solve the problems and different approaches. So today we're just going to look at one approach, a way of thought on how to, when you look at a problem, what are some of the tools and thinking that goes behind solving your problem. I know as a data scientist, you're always itching at, when I'm going to throw the neural network, when I'm going to throw my random forest, and etc. But before you get to that, there's a lot of work that goes into thinking about a problem, thinking about the data, thinking the properties about data, and then which method, formula, etc. that applies well to it. One of the things that I learned through my very short career and interesting read was like the data generating process is one of the most important things that you have to learn. It doesn't matter how good you understand your neural networks, how you can tune them. That's an important skill, yes. But if you don't understand that this is the data that I have, this is how it's generated, this is the limitation, this is the characteristics of the data, then you're sort of like on a shortfall. There's a lot of argument between you. As long as I have enough data, I don't care, But if you work for a business, like I do work for a bank, you could go make a prediction, and then whoever you're going to give that prediction to is like, how was this generated? How do you reach this conclusion? If you're not able to explain that from a business perspective, so you've already failed in your first role. So today, let's look at one approach that probably will be very good for attacking this particular problem. So I like to start with what's you probably have heard about this, called Bayesian reasoning. I know there's naive-based algorithms, but before you get into the algorithm, looking at the Bayesian way of reasoning and why I think it highly applies to this particular problem. So if you've done your math and you probably came around this formula, which to simplify it, it means that what's the probability of something happening based on what has happened before? What's the probability of it raining if the clouds are gray? And you can have multiple conditions. What is the probability of it raining when it's June and the clouds are gray? So that's the very basis of Bayesian reasoning. There's something here which we will look at here, known as a prior probability, and why it's the most important thing in a Bayesian way of reasoning. So forget the math, forget the formula. Let's get into the thinking, the reasoning, why this is a very good approach at solving this particular problem. So this is the map of Nairobi. This is a 2D map that's here. So let's say you're craving fast food, or you're an addict of fast food. So you go through several fast food chains, and then you end up at a big square. And then you decide like, okay, I want to map all locations where Big Square are. So I know currently they've added more stores, but like, okay, they have one in Karen, they have one in Junction, one in Lavington, Oval, and etc. So given that you can only eat at Big Square, what is the logical thinking after having this map? Which is the closest Big Square store to where I live? So if let's say you live in this area called Waithaka, you'll be like, okay, maybe Karen and Junction, I could go to either of those. But if I live, let's say, here, I'll probably go to the next one. There's a high and likely chance that I'll move from Adlife and come and eat in Karen, unless there's other things I'm going to do there other than just eating. So let's hold that thought while we're looking at this map. So if I switch next here, and I became a bit nerdy with this, so this is the same locations that I had before, but now I want to know if let's say I want to create an algorithm, if I am in Isile, which is the closest store or outlet should I go to? So this is known as a Voronoi diagram. What essentially it does, it makes this store your center point, right? And based on the next store to it, or the other stores to it, it partitions your area into equally spaced. So you realize the distance between here to here is the same as here to here, the same as here to here, and the distance between here and here, so it is the same as here to here. So if I find myself in any of this, I can partition my Nairobi area into this area. So if I find myself here, my formula or my algorithm will tell me, okay, go to Shell Mombasa Road. If I find myself here, I'm in kind of a quandary. I don't know where to go. But if I'm here, if I'm here, the closest will always be this, because this is the center point for that. Okay. Let's also build that into our mind. But what happens if one store is closed? Or when they were starting off, maybe. It means that, for example, if they only had 4 stores, and these are the ones, it means now, if I'm here, I have to travel longer to get here. The more stores they open, the less area I have to travel. The more my area gets partitioned more. So if these were 3, you can see the area I need to travel is long. The more stores that get added, the less area I have to travel. And back to our original map. So why are we here, and what does this have to do with Bayesian reasoning? All of you probably are on WhatsApp groups for weddings, funerals, and any other random things, correct? What informs the amount of money you give? Any answers? Yes? How other people contribute? Okay? The closeness to that person, right? This is this whole concept of Bayesian reasoning. In behavioral economics, they call it anchoring and adjustment. When you go and one person is given 1,000 shillings, that 1,000 shilling becomes the anchor. People will always contribute within that 1,000 shillings. Or if someone important or close to the family member says, like, I'm giving 10,000 shillings, someone won't go and say, like, okay, based on your abilities for earning, I'll give 50 shillings. It's so far off from that. So if you look at an average, like the first 3 people put 1,000 shillings, that becomes the anchor for that. And that's what we call, in Bayesian reasoning, prior probability. Before you attack a problem, before you do anything, what's the probability of this event happening? So you take 1,000 shillings, and then you adjust it. So you say, okay, everyone is giving 1,000 bob, but I didn't like this guy, so I'll give 500 shillings. So everyone puts 1,000 shillings, like, it's kind of my friend, I'll give 1,500. So you anchor and you adjust. So the anchor is being set. It's like one of those, they call those people find salvage ships that are sunk in the sea, they're looking for lost treasures. They go with a big ship, they anchor somewhere in the ocean, and then they have like a smaller boat that patrols the area and goes down to find everything else, because they know once we are anchored here, this is the general area, so the sunk ship must be within this particular. And we'll go into the code and look at this. If these were the hotspots of accidents, my anchor would be, if I cluster all hotspots, I better off have my ambulances very close to this hotspot. So location, the cluster of location becomes my anchor. My anchor is not necessarily weather data. We have 2 weather seasons. So what would I do when it's not raining? We have road segment data, zebra crossing and etc. Would I consider that? But I can have my strongest indicator or my prior knowledge, what we call prior probability, is that where accidents happen. Then now I can adjust using other information. I know this is where accident happened, good. Second thing, from the challenge, remember, if one ambulance, there's an accident, and let's just go back here to this example. So let's say we have 4 centers, accident centers, and then an accident happens here. Then an ambulance has to respond to this accident. What happens to the remaining ambulances in this area? It's very similar to Big Square taking off one of their stores offline or under renovation. It means now you have to travel farther to eat your food. So it means that the remaining ambulance has to cover a much more wider area because now they have to attend. If there's any other accidents happen after that, the remaining ambulances have to cover that particular area. So it's a dynamic changing scenario, which means that if we recompute our cluster center, it moves further up, or it moves further down, or it moves further area, which is an ambulance has get serviced, then now the remaining ambulances have to be redistributed. Okay? Great. Feel free to ask any questions. I'll go into the code in a few to show some of the things that I did to create this. My approach was that my work is to create that prior probability for you, that prior knowledge. Then you adjust it. Do you want to adjust it with road information? Do you want to adjust it with weather? And how do you think weather affects accidents? Do we have more accidents when it's raining? Do we have less accidents when it's raining? Do we have more accidents when it's dry? I think people drive slower when there's bad weather, so that you're more careful. It's slippery. You put on guard that you have to drive slowly. So I think actually when it's dry, we have more accidents. At the back.
In as much as when it's raining, you will drive slower. There are other factors like when it's about to rain, people will cluster on certain roads. So, and most of the time, hotspots are usually roads that are maybe frequently used. And then there are cars, sometimes when you're driving, there are tires that are not as good. So that means yeah, so other conditions will make it more easy for you to be on accidents as well. So I'd still go with what they've said. Yeah.
I would counter that by saying, when there are more cars on the road, there's less chance of accident. It's hard to have accident in a traffic, right? And we can just overlay the raining periods and the number of traffic accidents, right? And the reason why this is very important to discuss this, sometimes we carry our biases when you're analyzing data, right? We should let the data speak for itself. If I put myself back and, okay, does it make sense? Because accidents happen the whole year, right? And if we have a spike in April and have another spike in August, then we could say, like, there's some correlation, hence weather has some effect on the number of accidents that there are. But so I think the number one thing, go ahead.
I was just going to say data solves arguments. Let's figure it out.
Yeah, so yeah, we have the data. So the first exercise, we plot a timeline of number of accidents and the weather amount of precipitation that we have. And we have that in our data set. After that, we get a signal or an indication how much it affects that, and that we're going to use. Then we use that to adjust, right? So if there's more, and this is another thing. If there's more precipitation here than here, right? So we can decide, this is where initially we're going to place our ambulances, correct? But because it rains here more than here, and we know that the rain affects that, it's better we move this ambulance here because you expect more precipitation. And I was looking at the data, and I was like, hold on. Do we have different precipitation in Nairobi? So it might be a valid concern that Karen and Mombasa Road. True or not? So we'd say that we have more accidents happening in Karen than in Umoja. Would you make that argument? There's also another part to it. Karen is a higher ground. Does it ever flood in Karen? But usually floods in South C, South B. So we're likely to have more accidents and cars stuck on the road. That. Layer your understanding into the problem. Don't dive into the data first. Okay, road features. Do you think road features affect accidents? Recently at Sachangwan, they put in a road barrier similar to the one in Wayakiwe to avoid head-on collisions. Okay? So yes, some road features do affect accidents, but there's a zebra crossing effect. Accident is a well-lit road, cause an accident, a dimly lit road, lack of signage, etc. does it. Even if it does, it's a very small degree. One of the things that I started looking at, which is very obvious, is to ensure that an ambulance travels at the very minimum distance from where it's placed. And then other assumptions I was building into the data was that, because from the data, like we're looking at every 3 hours. So we assume that if an ambulance is committed, it won't be available for the next 3 hours. It's been taken out of the duty roster for serving people. And then another thing was like, once I created those tessellations or Voronoi diagrams, an ambulance only travels within its allocated sector. It doesn't move and go to another sector, because if that assumption is violated, then the problem becomes a completely different problems. So I use Collab. If you've not used it before, it just allows you to host your Python notebooks. I usually have problems installing packages on a local machine, and I hate it so much. So Collab just helps me to do that. So here, of course, we install all the libraries that you need, and we're going to step to them one at a time. If you've used Collab before, so it's hosted on your Google Drive. So there is a package. It just allows you to upload the file. So the first thing is to run this cell. So it runs sort of like you've used a Docker file. So it creates a container. So just quickly show you this if it's not important. Okay, I'll jump it. So the very first process of doing any analysis is doing an EDA, or what we know as exploratory data analysis, understanding the features and characteristics, distributions of the data that you have. So definitely the primary data we have here is about the accidents. And you can see this is the time an accident happened on the latitude and longitude where the accident happened. And then they just create a unique identifier, which is just a serialization from 1 to 6,318 number of accidents that are there. So this is a visualization of road segment, but allow me to get back to this. So here is the first that. So I took the accidents that happened, and the first thing I wanted to know. So this is from 2018 up to 2019. Aggregated the data by month to see if there are any trends for that. So definitely, there are less accidents in 2019 than 2020, and this number of accidents go down. Why this is important? It gives you an overall. If we had more data, it would be preferable if we had like maybe 6 or 7 years data, because it tells us there are other measures perhaps the government is taking or that we don't know about that's affecting the number of accidents that we are experiencing. So are we expecting more accidents? Are we expecting less accidents? So you can see the trend line is going down, but this is just 2 years data, so we don't have enough to make a conclusion about that. So this is the same thing, done this per day, looking at if there are any spikes. And definitely you can see there are certain spikes here, and this just tells you that you expect more accidents on Fridays and Saturdays for that case. So if that date is a Saturday, you need more ambulances. Friday, Saturday, you need to allocate more ambulances or a certain area for that, and we're going to come to that. And then did this similarly per hour, so each hour of the day. So this is about 6 to 7 p.m. This is where you expect more accidents, and I'll explain why this is important. And did it again now because we're looking at 3-hour sections. So every 3 hours, so starting from 0, the next 3 hours, the next 3 hours. So we're still at this point where we are locating. So if we have a fixed number of ambulances, we don't have the flexibility of getting more ambulances. This does not help. But if we have the few accidents, where are all these more accidents happening? So this is another information. This is sort of like what did Einstein call it? SpaceTime problem, or space-time continuum. It's a problem that's both affected by time and space where you are. And let me quickly come to where, so I took the same data, and I decided I want to cluster the accidents. So this is a method called the elbow curve methods. It tells you if you have scattered data, what's the optimal number of clusters that you can obtain. If everything is clustered around the same place, probably this curve would go something like this. So the section where the curve starts bending or flattening the COVID curve, when you're getting to the 5, it tells you, actually it's about, yeah, so this tells us how many ideal clusters I should have. So it's between 4 and 5, because that's where it starts flattening off. You can read more about the elbow curve method and the score that it has and how to obtain the number of clusters that you have. So knowing that we have that, so this is now the clustered maps, I mean the accident spots, and they're colored given the clusters there. So these are all accidents that are clustered as the same cluster, similar to this, similar to that. They're all different. This is different color to this, although it doesn't show clearly. So I've obtained my clusters, or I've allocated each accident to a cluster. So what I need to do next is to find that cluster center. Like we had that big square outlet for a case. So if I go down here, so now it tells me like, I decided I'm going to have 5 clusters based on the elbow method. I've visualized my cluster on the other side. And so remember, this is the longitude and the latitude. We can easily draw the map of Nairobi over here. So it tells me these are my cluster centers. So I have my priors. So if I have 6 ambulances, and now I have 5 clusters, how would I allocate them? Remember, I'm trying to minimize my distance to the accidents. So what helps me make that decision? So I have 5 cluster points and have 6 ambulances. So if I allocate an ambulance to each cluster, I'll have 1 ambulance that's hanging, correct? But now I would build a Voronoi diagram here, right? And one of the fancy things you could do, you can calculate this area. You can calculate the area that each ambulance hold. So definitely this would be, I think this one is the smallest area. This would be the smallest one. I mean the second smallest, followed by this and that. I'm on but this and that. So I will deploy 2 ambulances here because this ambulance here has a wider area to cover. Okay? So I'll allocate that the 6th extra ambulance here. And what I'll do, I'll find the optimal or the center point. I'll probably put it here, or I'll probably place the ambulance here. So now what do I have? In the challenge, you have time and latitude and longitude, the data you're supposed to submit. Going back to the data that we had, this is in essence, if you think about it from a machine learning perspective, I'm doing feature engineering, okay? So initially we had the date when an accident has happened and the latitude and longitude where it happened. So the next feature I have here is a cluster label. So this are those tessellation areas that I created. So this accident here, placed in this cluster. And this lat and longitude, this is now the center of this cluster, okay? So, adding another thing. So here, I should put it this way. This is the hour where the accident happened, okay? This is just extracted from this daytime. This is the hour. And what I did from that previous data that we have here, since we know that the accident, certain accidents happen, certain time has a lot of accidents happening, what in essence I'm trying to do is to take this two-dimensional picture and say like, okay, I know these are my center points, but there are more accidents probably happening here. Although this covers a big area, there are more accidents happening in this much more smaller area. So I'll go to my data. Yeah, this column here that I called IDX here, I have the number of accidents happening. So in this particular center, governed by that area, these are the number of accidents happening. Some of these are NA because I think I have some coding error here that needs to be collected. So now I have two things that drive accidents or things. I will probably, in this area, I'll deploy in this particular sector, sector 1, which has about 342. It's probably good to have more ambulances here as opposed to where it has less. Oh, it's disappeared. I was hoping to have more. But since you're running out of time, this has been shared, and feel free to shoot me any questions, either online, and I'll also be around, is that I have two priors, or my prior probability, or my prior knowledge that I need for that. So the question to you is, this is the first spot I'll consider. This is the person who put in 1,000 shillings in the group, this longitude and latitude, right? How many features can you have here, and how will that adjust here? And remember, if you think about it in a crazy way, the only thing you're doing is adjusting latitude and longitude, given any other information, right? Probably already have very good priors to use where you're going to place the, and then another thing that now is the coding challenge is, if it's, let me quickly go to the submission, and quickly go here. So we have date, so these are the 6 ambulances, so each ambulance has a latitude, longitude, latitude, longitude, up to the end, right? This is the time. Once this ambulance is committed, this is ambulance 1. Once this ambulance has been committed to that particular center, that latitude and longitude, what does it do to this other? It's the same time. That's what I was talking about, time and space. So remember how big square takes away one store, and then the center moves farther away, or you have to travel further. That means you have to reallocate this, although it had an initial center point where it was, but once this is, okay, at the start, all the 6 ambulances can be deployed at once, okay? Okay, maybe to simplify the problem, I'll think about that way. Number 1 challenge, take the center points, yeah, and just feed them here. Check the accuracy here, okay? Just using the cluster center points. Are they very close enough? Will it minimize the distance that an ambulance has to travel? You may discover that it's sufficient. I didn't test it myself, but you may discover it's sufficient, okay? But if it's not sufficient, I would say, remember, you can extract and say whether this is a Friday, this is a Saturday, this is a Sunday, and etc. So you expect more accidents at that area, which means you expect the ambulances to do more trips for that. So how do you adjust the latitude and longitude given the time? Thank you very much.